Over the last 3 lectures, we've learned a pleasantly small number of things. We learned that if you try and maximize or minimize some integral of a functional, then the functions involved have to obey something called the Euler-Lagrange equations. We then learned some physics, that there's this thing called a Lagrangian, and that if you integrate that over time, you get a quantity called the action, and that basically all systems in the universe act and evolve in order to minimize the action. This is called the principle of least action, which is also Hamilton's principle. It's also useful in a calculational sense, and we discovered in our 3rd lecture many examples of ways of following a nice simple recipe to use the principle of least action to do mechanics problems simply. And that recipe was simply 1, choose your coordinates, 2, find your Lagrangian in those coordinates, and 3, write down the Euler-Lagrange equations. Today we're going to work on having a look at slightly more general cases where you deal with Lagrangians, and then we're going to introduce an entirely new form of mechanics called Hamiltonian mechanics. First off, let's consider a problem that should be very familiar to all of us. Just imagine that we were constrained to move on the surface of a large sphere. And what's more, this large sphere was in fact rotating at some constant speed, maybe 1 revolution per day or something like that. Then obviously if we were on that rotation would have some kind of effect. Imagine that we can be pushed around on the surface of this thing by forces that we could describe by some conservative potential as a function of just the angular coordinates. But other than that, we're forced to stay on that surface. Right? Work out the equations of motion for how you would move around on that surface.